at the very beginning of time, you know, the Greeks were sitting there playing with chemistry. Chemistry's been around for a long time. Concepts and the things, the knowledge that we've learned over time. I mean, we're so much better today than we were then, of course. You know, so the first concept of the atom actually came from the Greeks initially, and the word atom itself is derived from a Greek word meaning invisible. So atomos is the word. And later on, other philosophers decided to talk a little bit more about the elements, you know, and so they basically decided that matter consisted of the four elements, four basic elements: the earth, fire, wind, and water. Say air and water, right? I was thinking about, you know. So later in life, around the 1800s, Dalton comes up with a theory. And Dalton's theory basically is composed of, you have to excuse my numbering here. Oops. Forgot how to count there. So matter is composed of exceedingly small particles called atoms, right? And the atoms is basically was perceived to be the smallest unit in a chemical change. And so an element consists of only one type of atom. And an element, today's term, an element is, again, one type of atom, and it's what is normally seen in the environment or in nature, okay? And so that element is perceived to be exactly the same for all atoms, or all atoms of that element are going to be exactly the same. So this is a copper penny. So pennies before 1982 were all copper. And so it was calculated to be about 3 times 10 to the 22nd copper atoms in a single penny. So you can see a single penny has a whole lot of copper atoms in it, right? So atoms of different elements, they're going to differ in properties as well as some of the characteristics about them, okay? And a compound consists of 2 or more different atoms. And they're going to have a ratio associated with them, and regardless of how much you have of that particular compound, that ratio is going to be consistent. Okay, and so the last thing that Dalton had said was that atoms can't be created, nor can it be destroyed. So in a chemical reaction. Instead, the only thing that you can do is rearrange them for different types of matter, okay? So does that make sense? Can you visualize it?
Yes.
Okay, good. Okay, so here's an example. So we have copper 2 oxide. Copper 2 oxide is made up of 2 atoms, 2 different atoms. So is that an element? Or is it a compound?
Compound.
Okay, good. So I'm going to introduce another term since we're talking about terms. My coffee hasn't hit yet, so you got to bear with me a little bit. So a molecule is two or more atoms. Okay. So based upon the definition of a molecule, would this be a molecule?
Yes.
Yes.
Okay. Okay, so in a chemical reaction, let's say we had oxygen and copper. And over time, with a little bit of energy added, we can set up a chemical formula. Copper metal, which is shown here, plus this here's oxygen gas. So what do we know about oxygen gas?
It's
Hello?
diatomic.
Say it again.
It's diatomic.
It's diatomic. So we always are going to write it as
O2.
O2. And this is going to make a compound, copper 2 oxide. Is this balanced?
No.
So what do we need to do to balance it?
You have 2 oxygen on one side, so you need 2 oxygen on the other.
Okay, so how do I do that?
So you put a 2 in front of the your product, and then you have to put another 2 on the copper alone. So that should be 2, 2 and 2.
Okay. So it gives me 2 copper here, gives me 2 copper over here, and 2 oxygens here. Okay, so it's balanced now?
Yes.
Okay. So from 2 pure substances, we end up getting a compound. Okay. So, and also if we take a look, are we generating a special atom here or anything like that? Or are we just changing things around?
Just changing things.
So we're just changing things. So we're obeying that law, which is also called the law of conservation. Again, what we put in, we end up getting out. Okay? The amount that we put into the reaction is what we got out of the reaction. Okay? So that's the law of conservation. That's going to be the premise of chemistry. Okay? And you're always going to make reference to it. You're always going to come back to it. Okay? Good? Okay, so the law of conservation of mass, what you put in is what you get out. That's pretty much how I like to think about it. And if you also think about the way it's written, you're neither creating nor destroying anything during a chemical change. You're just changing them around. At the end, what you put in there, you still should get out, okay? So the total mass that you're putting in there, you're still gonna get out in that product, okay? So that is gonna be the law of conservation. The quantity that you're putting in there should be the quantity that you get out. Questions, concerns? Okay, so we have the law of definite proportions, or the law of constant composition, same thing. So this basically tells us that we can set up a ratio between two two compounds, regardless of, of the elements, the mass of the elements in a compound. So, for instance, here we have a composition of isooctane. And so we can measure it, and we have the mass of the isooctane. So the amount of carbon is 14.82. The amount of hydrogen is 2.78. So the law of constant composition says that regardless of how much I have total or how much I have, I should remain with the same mass ratio. Or if you look at it, it'll be the same molar ratio between the two, okay? So you're gonna end up with the same composition regardless, okay? So it's 533 grams of carbon to 1 gram of hydrogen in all of these cases, okay? So that basically says that if you think about it, if we had water, and we looked at, regardless of how much water we have, that mass ratio should be exactly the same, okay? Because we know that we're always gonna have 2 hydrogens to 1 oxygen, okay? So here, if we're talking about copper, if we were talking about copper chloride, right? So this here tells us that we'd have a ratio of 2 to 1. Right? So, so in one case we have copper, we have a copper chloride. The other one, so we have a brown solution of copper chloride, and we have a green solution of copper chloride. Now, because of the color, we would suggest that there's probably something different about that copper to chloride relationship. But if we look at the numbers here, right? So we basically got a 2 to 1 ratio of the copper to chloride. So in one case, we have this guy. It's going to be copper 2. And in one case, this guy is going to be copper chloride, copper 1 chloride. Okay. And that would be the distinction between the two compounds. Green one, copper 1. Second one, copper 2, meaning that we need 2 chlorides between them. And so this here basically shows you exactly that. That's what you're going to have in this case. And then that's going to allow the altering between the 2 colors. Sorry, it should be not copper 2, it should be copper 4 and copper 2. Okay, so now at this point, Dalton's theory was pretty accurate so far about everything that he said, right? Can you think, well, knowing what you guys know, we've talked about protons, neutrons, electrons. What makes Dalton's theory a little bit questionable?
I think the first law, right? Because he says the atom is the smallest matter you can get. But then there's protons and neutrons and all that.
That could be broken down. So yeah, so the first law is kind of iffy, but there's even more to it as well. That's a little bit iffy, right? Because we've talked about protons, neutrons, and electrons. We've talked about how you balance those and everything like that, right? And we also talked about how the proton basically defines the atom. Have we not talked about that? On the periodic table, when we were talking about the periodic table. Are you guys there?
You're
The
talking
atomic
like
number.
mass number and where it lies on the periodic table based on the number of protons.
That's right.
Yeah.
Yeah. So yeah, we've talked about those, right? You remember that, right?
Yes.
So now I want you to still think about this stuff, and we're gonna, after I talk about it a little bit more, we're gonna see how things may alter here. Okay. So Dalton basically kind of established that baseline, right? And then Dalton basically, you know, it started kind of getting to think about a couple of things. So what are atoms composed of, right? And that's where we get into that proton, neutrons, and electrons. Because at first, Dalton, you were saying, Dalton said, oh, it's just the atom, that's it. But we know that there's smaller components of the atom, okay? And then, and the way that this was determined later on, scientists, they were kind of questioning it. You know, hey, Dalton's right about a lot of stuff, but hey, there could be some other things that he's wrong about. And so some of the experiments that were done, one was done by J.J. Thomson. He basically did the cathode ray. And what he did, he basically sealed the glass tube, which that basically he removed, he got rid of all of the air, vacuumed out all the air, so there's nothing in it, okay? And then he put in 2 metal electrodes. And when high voltage was applied across these electrodes, there was basically a visible beam. And they basically called that the cathode ray. And so from this, there was like, okay, so obviously there's something here, right, that's causing this to happen, right? That between these, the fact that we have these 2 electrodes that are existing, and now I can see this beam shooting across the electrode. So have you guys ever watched Frankenstein, the old Frankenstein movies where you had the 2 towers and the electricity going between the 2?
Yes.
Yeah. Okay, so that's essentially what they did, right? And so because of it, right, it made you sit there and think about it. Okay, so what's going on with that beam, right? And so in one case, we're getting a positive charge. In another case, we're getting negative charges, right? So there are positive charges and negative charges that are existing in that context, okay? And so Thomson basically was able to calculate the charge to mass ratio based upon the rays that were being generated and the metals that they had used, right? So that basically let us know that there were negatively charged particles, right? Obviously, there's negative and there's probably positive charged particles in there as well, too. Okay, and so he was the first to recognize that there were these negatively charged particles, and that we call electrons now, right? So this is the cathode ray. This is the experiment that he basically had done. And by putting, in addition, he also had put a magnet on it and the battery, and then so he was able to deflect the ray. Right? So then that suggests that there was charge associated with it. Okay, so further to prove that there is an electron, so Millikan basically did an oil drop experiment. So he basically created microscopic oil drops, which were charged, and they were basically electrically charged. So the oil drops could be slowed and reversed by an electric field, right? So instead of dropping, you can kind of keep them suspended or slowly, or come back up, right? So suggesting that there's a charge associated with it. So if it's negatively charged, it's going to go towards the positive. If it's positively charged, it's going to go towards the negative. And so what he saw was that these oil drops were staying up top. And because it was staying up top towards that positive charge, he was like, what the hell? Okay, so now if I adjust this field, what's going to happen, right? So then he would adjust the field, and then he would also see that the oil would begin to drop. So that meant that you had these charged particles, and these particles were negatively charged, and thus proving there was electrons that were existing. Okay, so he was able to calculate the charge of each specific drop, and then that kind of gave him an idea of the charge of a single electron. Okay, and so a single electron is 1.6 times 10 to the negative 19 coulombs. Sorry. Okay, so now they start thinking about, okay, so there's something going on. There's in one case, they were saying, okay, so we have positive and negative charges that exist. So they were kind of thinking of it, okay, so we have positive and negative charges existing, like in a cookie, and that's what makes up that cookie. So here's matter, and a positively charged matter has more of the positive, and then a negatively charged matter would have more of the negative. And so then that's what's going to make it, and it was all kind of mixed in together. Okay, so that was one theory, one hypothesis. The other hypothesis was, well, you have all your positive towards the center, and then you have electrons that were rotating around it or orbiting around it, kind of like the way the Earth orbits around the sun, or in the case of Saturn's rings. Okay, so that led to a lot of other experiments, right? So was it that it was all mushed together, or was it some type of organization? And so Rutherford basically had done an experiment, and so he basically aimed alpha particles. Alpha particles are positively charged particles at a thin piece of gold foil, so thin piece of gold metal, right? So then these particles he saw were being deflected, right? They weren't going straight through. They weren't attracted to it. They weren't just staying there. They were being deflected in so many different ways. Okay, so and this is basically showing you that experiment. Alpha particles going in, deflecting off the foil. So what do you think it was deflecting? Why was it attracting?
Because it hit the nucleus, because it's positively charged.
So because it was hitting the nucleus, and we know that if you have two people that are both positively charged, or if you have not two people, if you have two positively charged things, what happens?
They deflect.
They deflect. They repel each other, right? So you bring two positive poles of the magnet together, it's pushing against each other. They try to deflect, right? So that's exactly what's going to happen. They're going to deflect, okay? And so it deflects off, and then that proves that there was a positive center to that atom, right? And so this is what he basically said. He says, so there's a nucleus, and in that nucleus, it's positively charged overall. So the negative part of it must be surrounding the outside, and then that center must be composed of protons, right? And which we found out later on is that there is a center that is composed of protons, but not only protons, okay? So this just basically shows his results. So as it hits the nucleus, it deflects off. And so it's going to be deflecting in all the different directions as it's hitting the nucleus, Okay, it'll go straight through if it's just going through the electrical charges, but if it's hitting that nucleus, it bounces off because there's positive poles in the center. Okay, so the next thing was that they start finding elements or atoms that were the same element, but they had different masses, right? So then that led to the discovery of the neutrons. Okay, so they later discovered that all of the neutrons were found in the center of the atom and everything was good to go. Okay, so we're composed of three components, right? We have electrons, protons, and neutrons. Now, isotopes are basically atoms, the definition again, atoms that are the same element but have different masses. And those masses that change in mass is a result of the number of neutrons changing, because the atom is going to be defined by the number of protons. The number of neutrons adjusts the mass. Okay, so let's go a little deeper in here. Sorry about the history lesson. I'm not a history teacher, if you can't tell, but I have to give it to you. It's part of the class.
I'm liking this class now.
You're liking the class because it's history? This is the
Yeah.
worst part for me. I just like getting to the math, and I like the meat of meat. Give me the meat, you know?
Mhm.
Screw the sides, you know? I don't eat the salad. Just give me the meat, you know? Okay, so in terms of the atomic structure, right? So we have, in the nucleus, we have the protons and the neutrons. Now, protons and neutrons make up the mass of the atom, okay? So I told you guys I weigh 220, probably said it 150 times, okay? So if I put a speck of dust on my shoulder, is that going to change my weight?
No.
No.
No. So the electrons are equivalent to that speck of dust on me, right? So the electrons are so much smaller and weigh so little that it's not going to affect the weight of the atom itself. So the only thing that's contributing to the weight of the atom are the protons and neutrons. Okay, you guys got that?
Yes.
Okay. So in terms of the diameter of an atom, it's going to vary between atoms, but approximately 10 to the minus 10th meters, right? Which is really, really tiny. Okay. So the diameter of the nucleus is about 100,000 times smaller, which is 10 to the minus 15 meters, roughly. So a nucleus is really, really, really tiny. Okay, so in comparison, you know, because we can't really understand it. So in comparison, here's a football stadium. The nucleus is about the same size of a single blueberry in a football stadium. Can you see a single blueberry if you're standing at the very top of the stadium on the middle of the field?
No.
No, you can't, right? But that kind of gives you an idea of the size comparison, right? It is huge, relatively speaking, right? So the atom itself is so much bigger than the nuclei, okay? So that brings us to the fact that we can't see crap, right? Remember we were talking about macroscopic and microscopic and all of that? That's the reason why we need those instruments, because to see a single atom, it's impossible to do with our eyes. It's impossible to do with a microscope. It takes specialized equipment like an electron microscope or a tunnel scanning microscope. Okay, so we have protons, neutrons, and electrons, right? Okay, so units, the way that we're going to be measuring units, we often will say grams, right? So an atom and its subatomic particles are really, really small. So a carbon atom weighs less than 2 times 10 to the minus 23rd grams, right? So you'll never be weighing a single carbon atom on a scale. An electron, we've already talked about the charge, is less than 2 times 10 to the minus 19 coulombs. And then, so what we typically measure, the units that we use are AMUs, atomic mass units. Because it's so small, we're going to need smaller units, okay? So 1 AMU is equal to 1.66 times, 1.6605 times 10 to the minus 24 grams. And so the mass of a carbon atom is, carbon 12 atom, is equal to 12 AMU, okay? So the mass of carbon 12 is 12 AMU. If you look on the periodic table, that's essentially what we're given, is that AMU, right? 12.0001 AMU, being the average of all of the carbon atoms that exist. Okay. So, and then we know the fundamental charge on an electron, 1.602 times 10 to the minus 19. Okay, to get more precise, a proton, the mass of a single proton is 1.0073 AMEs, or we just say 1 roughly, right? So it has a charge of +1. The mass of a neutron is 1.0087 AMU. It's slightly heavier than a proton. It doesn't have a charge associated with it. And an electron is 0.00055 AMU. So you guys can kind of see the difference between 1 and 0.00055, right? Big difference between the two, right? Kind of like me and a speck of dust, right? Okay, but an electron has a total -1 charge, okay? Piece of cake? Are you with me? Are you asleep?
We're here.
Yes.
Okay, so we've talked about atomic number. The one thing that I want to add on to that is we use for atomic number Z. So if you see the letter Z, that's making reference to the atomic number. So the atomic number Z, then you have to give them the atomic number. Okay, so can you guys give me the atomic number of vanadium?
23.
Okay, so how many protons does vanadium have?
23.
How many electrons?
23.
And how many neutrons? That's correct. Okay, can you tell me how you calculate that? So we remember from last week, we kind of talked about this, if I remember correctly. So protons are going to equal the atomic number. Because atoms are neutral, in a neutral atom, protons equal number of electrons. Mass number equals the whole number of the atomic weight or atomic mass, not mass. And mass number also equals number of protons plus number of neutrons. Oops. Or we could say our number of neutrons equals mass number minus protons. Okay? Do you guys get that? Can you see it?
Mm-hmm.
Okay, so we've talked about this already, right? So I'm not going to spend a lot of time on it, but let's do a couple of test runs. How many, so bismuth, what is the chemical symbol for bismuth? What is the number of protons and the atomic number? Let's see, who will I pick on?
Bismuth.
What was that?
Bismuth.
Bismuth, that's correct.
And you wanted what for it? The symbol?
I want to know the symbol for bismuth,
Bi.
okay? And what is its atomic number?
83.
And what is its number of protons?
83.
Number of electrons?
83.
The atomic mass?
I can't see this, but does it say 208.96 or 206.96?
It says 208.98.
So then 126 for neutrons?
So you're already giving me the neutrons. You're just skipping to the goal, huh?
I
So
thought
what
that's
is,
what you asked.
no, I said ask for the atomic weight or atomic mass.
Oh,
209.
208.98.
208.98. Now the atomic number.
126.
The atomic number?
Oh, the atomic number 83.
Oh, sorry, I went back to the old thing. I meant the mass number. It's getting anxious.
209.
209. And then the number of neutrons.
126.
Okay. And how did you calculate that 126?
You subtract the mass number by the number of protons.
Okay. So I have 209 minus 83. So piece of cake.
Yes.
Is there anybody who's having problems with this?
No. No.
Okay. So
No.
it will, did you say no? Any
Yeah, I
yeses?
said no.
Okay. Any yeses? Anybody having problems? Good. Okay, so we can keep going. Okay, because we have neutral atoms, your positive charge has to equal your negative charge. So that means your protons have to equal your electrons. Makes sense? So we've talked about your mass number. Okay, so let's talk about ions. So the definition of an ion is a charge, basically a charged atom. So it's an atom that has an electrical charge associated with it. We have two types of ions. We have a cation, which is positively charged. One way of remembering it, you see, cations are positive, right? Positively charged, positive. Ba-dum-bum. Okay, you guys don't get my bad joke. Fine. Fine if you're gonna be like that. Okay? An anion
It's a negative.
an anion is a negatively charged ion.
I like to think anion, anti.
Okay, so those are the two types. So the question is, how do you get a negative or a positive charge thing? Like, didn't I just tell you that atoms were neutral?
Yes.
So let's talk about that. Okay. So ions are a case where your protons are not equal to your number of electrons. Because the electrons are orbiting on the outside, remember we were talking about the center being the nucleus, the outside being the electrons, right? So we're able to get electrons on the outside or remove electrons from the outside of an atom. Because we're able to gain or lose electrons, right? This allows us to have that positive or negative charge. Okay, so for instance, if I have, let's say, sodium. Where's my periodic table? Come on. Okay, so I have sodium here, Na. Na has how many protons?
11.
11.
11. So let's say I removed a single electron from there. How many electrons does Na have now?
10.
10.
Okay, so if I have 11 positive charges and I have 10 negative charges, what will be the total charge on sodium?
1.
1.
1.
So Na plus, which is understood to be 1, right, means that we have 1 electron removed from sodium. Okay,
Like the cation.
so that is a cation. That's correct. Okay, so let's say I have, let's say we have fluorine. Okay, how many electrons does fluorine normally have?
9.
Okay, so it has 9 electrons. And how many protons does it normally have?
9.
9.
Okay, so it has 9 protons. So let's say fluorine captures another electron, so now giving it 10. So what would be the total charge on fluorine?
-1.
-1. So we put just a negative. Okay? So let's go with, say, cobalt. So how many electrons does cobalt normally have?
27.
27.
Okay. How many protons does cobalt normally have?
27.
Okay, so if I remove 4 electrons, what is going to be the charge on the cobalt?
3 plus.
It's going to be 3 plus. If I remove 4,
Yeah.
4 plus.
It's gonna be 4 plus.
okay, so we'd write it as 4 plus. So that would be the total charge on the cobalt atom, or that cobalt ion. So fluorine here, this ion, is it an anion or is it a cation?
Anion.
It's an anion, that's right. And this guy, the cobalt,
Cation.
Ion.
cation. That's positive, okay? Piece of cake?
Yes.
Yep.
Yeah.
Okay. Okay, so we've talked about the charge. You have a good idea of how that works, right? Talked about cations, we talked about anions. You already know about the symbols. God, I think I've already gone over this chapter without even realizing. Okay, so these are some of the commonly known elements, which you guys should know definitely by the end, right? And then some of them you'll realize that their names changed over time, right? Like copper, right? Copper used to be called cuprum. And gold was called aurum. And iron was called ferrum. So to kind of keep with tradition, we use those symbols because it used to have those old names, okay? So let's talk about isotopes. An isotope is, again, it's an atom that has a different number of neutrons, right? Which means that its atomic mass is going to be different, okay? Now, the way that we write this, there's a couple of ways that we write it. One way is here, where we put the new atomic mass up in the left-hand corner. So this tells us that that particular atom of magnesium is 24. This particular atom of magnesium is 25. And this particular atom is 26. So if they're so damn exact, how do we end up with, let me see. How do we end up with 24.305? What do you guys think? So if in nature, we have 24, manganese 24, we have manganese 25, and we have manganese 26. So if we have all three of those that exist in nature, why do we end up with, on the periodic table, 24.305?
The difference in neutrons.
It is because of the difference in neutrons, but when we talk about what's on the periodic table takes into account all of the different isotopes. And so it's averaged between all of the different isotopes. Based upon that number, 24.305, I would assume that we have more of the one that's 24 and less of the ones that are 25 and 26. But we know that they both exist, 25 and 26, because we have a number that is 0.305. That means that there is a percentage, a small percentage, that is going to be made up by those two different isotopes. But the bulk of it is going to be 24 magnesium 24. Okay. Do you guys get that? Or am I just talking out on the side of my neck?
I got it.
You got it? Okay. So on the periodic table basically gives us an average of all of the isotopes that exist in nature. Okay. So it represents an average. Okay. And if you look at the number that atomic mass is closest to, right? So for instance, this one is close to 24. So that's the one that's going to be the most abundant. If you take a look at lithium, which isotope of lithium? So it's lithium, I think it's 5, 6, 7 are the three isotopes of lithium. So it's lithium.
7.
What was that? So
Or
lithium 7. So 7 would be the one that's most abundant, right? The other two would be so little, okay? Okay? You guys kind of get that? Yes, no,
Yeah.
maybe?
Yes.
Yes.
Okay, so we have these numbers in superscript written in the corner. So this lets me know that the atomic mass for this is 23. What is its mass number? I mean, sorry, 24, not 23. 24.
24.
24. 24 would be its mass number.
Yes.
So let's talk about that. So if there's 24 is the mass number, then how many protons must it have? What is the
24.
4.
24 protons? Are you sure? We'll put money on it. Okay, let's go to magnesium.
Oh, it's 12.
Okay. So if we have magnesium 24, so protons, okay, so if we have magnesium 24, what would be the number of protons,
12,
number of electrons,
12,
12.
number of neutrons,
12,
mass number,
24, point
atomic number?
5.
24.5 would be its mass number?
No.
No, 24.305 for atomic number.
Okay, so we just talked about this. We're saying that its mass number, which is also going to be its atomic mass, is going to be 24, right? It's not going to be what's on the periodic table anymore because we're talking about the isotope. And remember, what's on the periodic table is an average of all of the isotopes together. Okay, now we're just talking about one isotope. So what would be the, the atomic number would be 12, but the atomic mass would be
24.
24. So do you get that, Maddie?
Yeah. Just too early.
Sorry. Not atomic mass, atomic mass. It is. It's way too early. I don't know what it is today. Okay, so what if we were talking about manganese 26? I mean, not manganese, magnesium 26. Number of protons?
12,
12.
Oh.
Okay, 12. Okay. Number of electrons?
12.
Number of electrons?
12,
Number of neutrons? Number of neutrons?
14,
Is that me? Is mine going bad?
No,
Is that me? Is mine going bad?
no. I think it's all of us. I think it's all of us.
Mass number? Mass number?
26. 26.
Atomic number?
12,
Atomic mass.
26.
26.
Okay. So I have two people answering the question. I know my class is bigger than two people. Do everybody else get it?
Yes.
Yeah.
Yes.
Yeah.
Okay. Anybody not get it?
You go over it again? Because I'm kind of like not understanding it.
Sure, I can go over it again. Okay, so when there's a superscript on the left-hand side, that's going to be your new atomic mass. And it's also going to be your mass number. Okay, so your new atomic mass is going to be 26. Okay, so normally, magnesium is 24.305. That would be the normal atomic mass. And that represents, so that mass there represents the average of all of the isotopes that exist in nature. Okay? So, but we've isolated just this one isotope. And an isotope differs in the number of neutrons that we have. The number of protons, which is defined by the atomic number, is 12. Right? So your number of protons aren't going to change ever for an atom. It's always going to be whatever it is. So all magnesium atoms, whether it's an whether it's an ion or whether it's an isotope, it's always going to have the same atomic number, which is also the same number of protons. So protons will never change, okay, for that atom. Okay, so then because there's no charge associated with it, then we know that it's neutral. It's a neutral atom. That means the number of protons have to equal the number of electrons. Okay, so protons equal the number of electrons when the atom is neutral, neutrally charged, meaning that there's not a plus or a minus over here. Okay, so the mass number, which is the same, it's the whole number of the atomic mass. So if the atomic mass has been changed to 26, so then the mass number is going to be 26. So that means 26. So we know that calculate the number of neutrons, we subtract the mass number by the number of protons. Okay, so 26 minus 12 is what?
14.
14. And that's how many neutrons that we get. Okay, does that make sense?
Yeah.
Okay, so let's test out one more. Let's say we have okay, so let's say we have this isotope. Okay, so what is the number of protons? Are you sure it's 35?
Yes.
Oh, that's sulfur. Oh, okay.
16.
Oh, wait. Oh, that's
You said
16.
You said what is the number of what?
Protons.
Protons.
Oh, okay. Well, yeah, if it's sulfur, it has to be 16. Only the number of neutrons changes, not the number of protons.
Okay, so we have 16. Number of electrons.
16.
Are you sure it's 16?
Would it be 18?
It would be 18.
Yeah,
Why is it
18.
18?
Because
Oh.
it's
Oh,
-2. So you're going to add 2.
That's right. It's a -2, so that means we're adding 2 more electrons. Okay. Number of neutrons.
No, it would be 19, wouldn't it?
Okay. And how
Yeah.
did you calculate that?
Because the composition would already have 16 if it was regular. So because it's an isotope, it has more neutrons. So that means it has 3 more because the mass numbers changed.
Okay. So, and what is the mass number?
35.
35.
Atomic number?
16.
16.
Atomic mass?
35.
35.
Okay. Piece of cake?
Yes.
What do you teach, sir?
You said the way I teach?
Yes, sir.
Okay.
Dr. Henry,
Yes.
I have a question about the ion part. So for the proton and electrons, how do we know how many of each there is? Or does that
Okay.
not matter right now?
No, it does matter, right? So, because we know that this is an ion, right? What kind of ion is
Yeah.
it?
It's a
What kind of
negative
ion is it?
An ion?
It's an anion.
Anion.
'Cause it's
Okay, so
negative.
Charge.
we know that it has a negative charge associated with it. So that means that we're adding electrons. So this tells me how many electrons I added to that. So we know sulfur normally has how many?
16.
16.
16. So if I'm adding 2 more, then how many do I have now? 16 plus
18.
2.
18.
Okay.
2 is 18.
Okay. So then that tells me the number of electrons. So does that answer your question?
So we don't take away protons and electrons.
No, you don't take away protons. Protons define the element. So your protons are never going to change. So the only thing that can change is your number of electrons or your number of neutrons. So number of electrons are going to change when you have charged, when it's plus or minus charged. Your number of neutrons are going to change when you have a change in weight, right?
Okay.
So this side represents your change in weight. This side represents your charge. And they're both
Got it.
superscript, right?
Yeah.
Okay.
Yeah, I understand that.
Okay. So let's give it, because I'm starting to I want to make sure that you guys got this. Okay. So let's say we have oops. Let's say we have uranium. And this is another way of writing it. Uranium 95. Oops, sorry. Uranium, not uranium 95. Uranium, that would be way too little. $236. Okay, so the symbol, the way you'd write the symbol, uranium 236, you'd write it U 236. So it just tells me the mass of it now. Or you'll see it written like this, just U dash 236. Okay, so 3 different ways. Or you'll see it one other way, 236, and then down here, we'd write it, we'd write the atomic number. So just remind us the atomic number. Okay, and that's particularly when you're writing, we're talking about a nuclear reaction. Okay, so these are the 3 ways to write it, or 4 ways to write it. Okay, just to confuse you a little bit. Okay, so let's say we have uranium 236. 6 plus. Okay, so number of protons.
92.
92.
Yes.
Number of electrons.
86.
Yes.
Number of neutrons.
92, right?
92.
No. Would we add just, I don't know, 88?
144.
144.
Or
Who said 144?
I did.
It is 144. So why is it 144?
Because you subtract the mass number minus the protons.
Okay, our mass number would be 236, right?
Yeah.
Okay, so 236 minus 92, 144.
Mhm.
The atomic number?
92.
Number is 92.
Atomic mass?
36.
Piece of cake?
Yes.
So the 6 after the uranium will only affect the electrons. It won't affect the protons.
That is correct.
Okay.
Say that again for the peanut gallery. So the 6 here affect what again?
The electrons, not the protons.
It affects the electrons, not the protons.
So the protons is always going to be equal to the atomic number.
The protons are always going to be equal to the atomic number. That is correct. Okay, questions? Concerns? Cash?
8.
Okay, ready to move on?
Yep.
Yeah.
Okay, so this is just basically showing you everything that we just talked about, the different ways of writing it. Remember me telling you about the whole thing being averaged over all three? This is basically showing you that. So this is for hydrogen. Hydrogen exists in nature in 3 different isotopes. We have hydrogen 1, hydrogen 2, and hydrogen 3. This gives you how much in nature that it actually exists. These are the AMUs. These are the actual atomic mass units. If you calculate the number of protons and the number of neutrons exactly, and you look, the number of protons never change, but the number of neutrons change for the atomic mass for hydrogen for each of your isotopes. Questions? Concerns? Cash? So what you see on the periodic table is just these guys, the number, its atomic mass, multiplied by its abundance. Added together, right? So you just multiply this by the percentage. So you multiply 1.0078. Can you guys do this for me? $1.0078 times 99 8 whoops 99.98 plus 2.0141 times 0.000115. And what do you guys get?
1.06.
1.00.
79. There's more, but they're like 2 and 0, so it doesn't matter.
Okay. So sig figs would work out to be about that, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. Although this would give us a much smaller sig fig. So questions. So isn't that approximately what you see on your periodic table?
Yeah.
Yes.
Okay. So to calculate, if you're going to be calculating the average mass in nature, right? It's just multiplying each one by the decimal form by its atomic mass. Okay, that's it. Okay, and that's what this is basically saying. So your atomic mass that we see on our periodic table is going to be the average of the isotopes that are occurring in nature. This basically shows you exactly what you guys just did, right? So it's the sum of the isotonic mass times the fraction of abundance. So in this case, 19.9% of B10, this is the actual weight, right? This is 80.1% of B11. This is the actual weight of B11. So if you do that, you multiply them by that number. So 0.199 times 10.019 AMU plus 0.801 times 11.0093 AMU, you're going to get 10.81 for boron. So if you look on your periodic table, what is the weight of boron? So does that work out?
Yes.
Piece of cake?
Yep.
Good.
Yes, sir.
Oops. Okay, so a mass spec is, it tells us the occurrence and the natural abundance of isotopes that can be found in nature, right? And so we often will use mass specs to determine how much of an abundance of a particular isotope exists. You can also use the mass spec to separate them, since they'll be coming out in different peaks. So some mass specs are really good, that you can actually play with ions in themselves, and so you can actually separate ions as well. Okay. So this basically just shows you that. Okay. And you guys will probably use more, hopefully we'll get a mass spec when we start OChem, or maybe if we're lucky and my budget gets funded, we'll have one next semester, so we'll have an experiment that we can play with this. So now molecular formulas. So we're going to be talking about structures and formulas. And you guys know that we're going to basically be using models. The stick ball model, because We can't really play with the chemical itself independently. So we need models to kind of represent those chemicals, kind of make it easier for us. And we use the chemical symbols to sit there and represent the chemical for us as well. So here we have methane. You guys should be very familiar with methane because we go to school in Kalinga. So you guys have heard of Harris Ranch. It's one of the leading sources of methane in the valley. Why is that?
Cow poop.
Cow poop or cow farts, right? So methane is a gas that comes out basically when you poop or fart. And so since there's so many cows out there, we get a lot of poop and fart, and we can smell it in the evenings. Right? So this here represents the methane molecule, or you could say compound, right? It is composed of carbon and 4 hydrogens. This is basically a structural form of methane. So this is our molecular formula, structural form. This here is called your ball and stick model. This here is called the space filling model. So why is this called the ball and stick model?
Because it's balls and sticks.
It's so funny. Every time that I try to ask for Siri, she don't respond. But I say some word, she just loves, if I say sir, or if I say structure, she wants to respond to that. Okay, so you're right, because it's balls and sticks, right? So that's the reason why we call it the ball and stick model. Piece of cake?
Yes.
Yeah? No?
Yes.
Okay. So these are all things that we've talked about already. You know about diatomic molecules, right? We know what a molecule is, right? So diatomic molecules have no fear of ice cold beer.
Yep.
Okay. So, and then we also talked about sulfur 18 and phosphorus 4, P4, right? So these are the ones that you need to be familiar with, okay? So this is the structure, the structural molecule for sulfur. So this is the ball and stick form. This is the space filling form. Okay, so when we're talking about the hydrogen atom, these are 2 atoms. This is the way we would write 2 atoms. This is what the hydrogen gas molecule will look like, H2. And then if we have 2 hydrogen atoms. So if you notice here, no subscript, no coefficient. That means you have a single atom. This one tells me I have 2 hydrogen atoms. 2 hydrogen atoms. This one tells me I have 1 hydrogen molecule. We have no coefficient in front, right? But we have subscripts after. It tells me how many of those hydrogen molecules I have. Oops. And then lastly, we have 2 hydrogen molecules. That means we have 2 of these, 2 of the molecules themselves. So we have a coefficient telling me how many molecules I have. And then we have the 2 here telling me that it's a molecule. You guys see the distinction?
Yes.
Yes.
Anybody not see the distinction? Okay. So that brings us to empirical formulas. And I believe this is a great stopping point